Hi, I'm Bob Westervelt, and for this week's Wednesday night seminar, Rick Keller will tell us about branched flow. Rick.
Thank you, Bob. So this I'm showing now is a draft of an article accepted and will be published in Physics Today, the physics organ journal of physicists in this country. And it's written at a low level, made accessible to physicists from all sorts of communities. And it begins with these two pictures. You already saw the branch flow coming from Bob's experiment. This may remind you of it. This is a theoretical simulation of a trajectory and wave, classical and quantum, passing over this random potential here, whose contour map is shown in green, which is high zone, and red are low zones. And you can see it smoothly and randomly undulating. And there's a very uniform set of trajectories or waves injected here, and the branching is natural. It happens. It should happen. And here's another example of it. This is the 2004 tsunami from Sendai, Japan. And NOAA has made a map of what the wave energy would have been in the Pacific Ocean. And you see its branch flow. What's going on here is that the tsunami waves, 100 miles wavelength, the wavelength is much bigger than the depth of the ocean. So the tsunami waves are traveling in shallow water. And in shallow water, waves travel proportional to the square root of the depth. So since the depth isn't uniform, there's a random potential like this one here, which tsunami waves feel. And I find it interesting and somewhat tragic that there was a bunch of energy made it to the coast of the US and somebody was killed here by inadvisedly floating around in his harbor while the tsunami wave arrived. And there were strong currents and he was swept away. But you can see how the non-uniform distribution. So what Bob has started is a whole field called branch flow, and it now has many, many applications, including, maybe I'll get back to that slide and I'll get back to this one, including microwaves traveling from pulsars through the interstellar medium and arriving at Earth. And the interstellar medium includes ionized gas clouds, and the ions refract the microwaves. And of course, the cloud is not very well organized, so it's a random potential. And what happens on Earth is, this is what would happen if we were able to image the whole field of arriving microwaves. But the Earth is passing through, because of the motion of the Earth, the proper motion of the Earth and the pulsar, the Earth is passing through these knots of intensity. You've seen this. Whenever you look at a pool bottom with the sunlight shining on it, you're seeing this early stages of branch flow. You all know this pattern in a way it moves across the pool bottom. There's another case where you probably don't know you've been seeing it, you've been hearing it. So if you are walking around outside, anywhere near civilization, you occasionally hear an airplane pretty high up. And you'll notice if it's not too high up, especially, you'll hear it do, I'm sorry for the sound effects, but here they go. It sounds like this. Now, do you think there's a drunken pilot doing this with the accelerator? No. What you're hearing is branch flow. What's happening is air currents are moving up. That itself causes refraction. There's different temperatures. That causes refraction. By the time the sound gets a mile or two down to the surface of the Earth, there's a pool bottom pattern traveling along the surface. And it's traveling past you. And when you get in one of these dark regions, it gets loud. And you get one of these light regions, it gets soft. So I discovered this making I just wanted to make it's not the discovery, I mean, this is well known, but I made a sound file of an airplane passing overhead for a course I teach on acoustics, a gen ed course. And I wanted to prove that sound of all frequencies it travels at the same speed. So the airplane is a broadband source. It's a white noise source, more or less. And I wanted to show that as it got louder and softer, that all frequencies got loud and soft at the same time, because they all arrive at the same time. They all refract in the same way. Refraction, you should remember for the rest of your life, is caused by wave speed variations with position. And that can be because the air is moving, the medium is moving, or it's got a different refractive index in different places. But always never forget that the wave refracts towards the slower moving waves. So there's faster and slower moving waves for whatever reason. If it's different from place to place, it's going to refract the wave. And this is what's happening on Earth. And I haven't got time to show, but absolutely gorgeous microwave data showing interference fringes coming from this pulsar and arriving at Earth. The interference fringes change every few minutes, and there's even larger changes over days and months. And they make a recording of a large range of microwave frequencies versus time. The time axis is minutes, hours, days. And so this is absolutely beautiful physics and another example of branch flow. It isn't published yet that this is branch flow, but this is a historical picture in the sense that there was a guy at Cornell, an astronomy student named Przybylski, who kind of realized it was branch flow. And this is his thesis from 1984. His thesis advisor was Cordes, and very well known in interstellar optics. And unfortunately, Cordes didn't like this. This is a picture of branch flow. Przybylski thought, well, maybe it's refracting like this through the interstellar cloud. And this is, by the way, the signal I'm talking about. These interference fringes wouldn't be there. This is a remarkable fact. Wouldn't be there unless the whole cloud, maybe a light year across, is coherently sending radiation across its whole width toward Earth. Coherently. How can that be? Well, the pulsar is very far from the cloud and is pulsing these microwaves toward the cloud. And by the time they reach the cloud, they're all spread out. And they reach the cloud with their phase fronts in phase, and it gets sent down to Earth after being scattered. And here's some of the evidence. Another use of branch flow, and this we kick ourselves all over the room for almost every day. But now we're happy. We've realized this. This is what happens in graphene at finite temperature to electrons that try to travel through graphene. It's branch flow. Now, why? This is perfect piece of graphene, but it's at some temperature. And phonons are running around, and they're collecting energy in one region and spreading out in the other region. And that affects the electron's wave speed. And you know the rest of the story. So we believe there's branch flow going on in graphene and other solids, causing the resistivity to be what it is. And it is known that phonons cause resistivity of pure metals, but not this way. This is a new picture which we've developed. And the reason we kick ourselves across the room is this is exactly Bob Westervelt's experiment, which we had done 20 years earlier with him, or we'd done the theory, except that what's causing the lumps is the sound waves, not the atoms that cause his electrons to live in 2 degrees of freedom. Otherwise, it's the same. Why did it take us so long? Well, one reason it took us so long is standard theory of electrons and phonons. It's completely different than this. What you're told is, oh yes, an electron can scatter off a phonon in a solid only if it creates one or annihilates one, and one at a time. And that's called perturbation theory. But what we realized was if you
Uh-oh. Let's we'll be back, I think. Think of some good questions. I'll with this break because Rick is being nice, but like I say, he's very artistic. And so if you want to ask why does that happen, then it would be good. Oh, oh, here he is. Hi, Rick. Okay, that's all right. I'll tell some bad jokes or something to. Okay, all right. So he'll be back in a minute. He said computer croaked on him. I'm not sure why, but it'll come back. Sounds like my house. Everything in my house doesn't work. So I also have a big hole in my lawn that's about this big around. I'm not sure what comes out of there at night. I'm afraid to look. It might have teeth, you know, like one of these movies. And we have coyotes too. I'm looking out the window here and I see a big coyote walk across my lawn. So it's getting to be a dangerous. But think about questions with branch flow and, you know, why, you know, what really does that mean and why does that happen? And get Rick back in shape. It's sort of halfway, it's between the classical limit, sort of where everything is totally no waves, and the quantum limit, and sort of halfway in between. It turns out that the phonons are bosons, and it's like light. And if you put a lot of photons together, they turn into an electric field. Okay. So if you have a ton of photons all in the same state, then you can define the electric and magnetic field and you're totally classical. So the quantum limit is classical, if you follow me. That is, you just put more and more photons into the same state. So that if you have a laser beam, something like that, it's very, very many photons in the same state. You can actually define an electric field and a magnetic field and just use Lorenz's equation in order to figure out the force on an electron. And it's getting toward that kind of transformation from being a single photon zipping along by itself and then lots going all together. That's how the phonons start looking like sound waves. I used to have a Chinese calendar, my wife's Chinese, and it tells you the good days and the bad days. And this might be a bad day to go out and have dinner, you know, because the restaurant will be closed and your car's tires will be flat and all of that will be, I think you should come back online pretty soon. Do you have any questions I can answer? Actually, I know a fair amount about this stuff. So.
I didn't realize that you were like just as behind this discovery as he was.
Well,
It
we
sounded
didn't
like
know. Yeah, we didn't know what we were doing. But what you'll find out some of the best things is when you don't know what you're doing. You know what I mean? And then you say, what on earth is that? And like I say, I thought this is going to be a disaster, of course. But then Rick rescued me. And here he comes. He's back. Oh, you look good, Rick. The different view of your
I'm back on my iPad. The computer died, but might come back, and I don't have the slides up on the iPad at the moment. But I don't know how much time we have.
well,
Bob?
not too many. You know what it might be good is that I think we talked about the same paper on Monday with the students in the course, and we were looking at some of the same pictures. And maybe it would be
Okay.
a good time for you to answer some questions about both, what you were talking about and sort of more general questions too. So let's, a good question as to what you'd like to. Hey, could
I
you
have a
say,
question.
go ahead.
Oh.
Go ahead.
Oh, it's more of a general question, but I was just curious about your website, Blockbusters. I thought it was really cool and I enjoyed looking through it. I was just wondering kind of what led you to make it, and yeah.
Which one? Which website? We have 2 or 3.
Oh, Blockbuster. I think
Blockbusters.
Yeah.
Yes. So we're very happy about that website, and branch flow is a big part of it. What has happened since actually I didn't discovery of flow, the images we found were so beautiful. You saw that you saw the covers of Physics Today and of Nature. I started to make art, and there's a lot of art you can make from this branch flow. And I did some other subjects, and I put the pictures outside my office in physics, and somebody saw them and said, "Oh, we have this gallery in MIT physics department. Could you put them there for a year?" I said, "Sure." And then somebody from MIT Compton Gallery saw them there and said, "Would you do an exhibit for us?" So I had 35 large images in the Compton Gallery for a few months or something. And then I had exhibits all over the country and the world. So this was all because of Bob. I wouldn't have gotten
No,
into
it wasn't.
So that website started out as an idea. Anton Graf, a student of mine, a graduate student, he said, we should make a really high-end website with this art and science. By this time, my postdoc, Alvar, and my other students, Ragnar Fleischmann from Germany, were making equally beautiful pictures, and we're combining these in an art science website where the science is real. It's got various facets to it, including papers you can look up, descriptions you can look up. There will be interviews of scientists. The idea is art and science is a big deal. It has been for a long time. It's getting bigger again, seems to come in cycles. But this one is different in the sense that the artists themselves are doing both the art, are also scientists and doing both things on this website. We're trying to promulgate branch flow and some associated things like this electron flow. And I showed you in graphene. And it's well, we're getting followers, and we got it on Instagram now, and all that good stuff. So what did you find out about it? How did you find out about it? I guess you mentioned it, Bob, is that right?
Yeah, I gave them a link to your site so they could see some of the pictures.
You just dropped out for a minute, but I think it's okay now.
Yeah.
So what do you think? I'd like to ask you. I mean, we don't have that many reactions yet. It's only a month or two old. What did you think about it?
Well, you're asking the students. Yeah.
The student.
Yeah.
I thought the images were really beautiful, and it was just really cool to see what you were doing at the intersection of science and art. Yeah, I was admiring the images. They were really great to look at.
So do you have any suggestions? Because we could talk later maybe, but what would you like to see? Because you're a perfect example of the audience we want.
As I was going through the website, I was looking for like an option. I was seeing if you could order prints from some of them, because some of them look really nice. And I was like, that would be so cool to have in my dorm. So that's just something I was thinking about.
Well, okay, I'm going to invite you and everyone to do something. I have had so many shows over the years, and what happens is they want prints made, and they want them made just right for their show, whatever frame or whatever. And I have a 3 dozen big prints sitting around my office at physics, also in chemistry, and also at home. So I've just given a bunch away to grad students. They were on they've been decorating the halls in physics, maybe 8 in physics
Right.
already. But how about your dorm room? I mean, come by my office and we can get them for you free of charge.
I will
But I have
definitely
stopped
pick you up on
selling.
that.
Okay, take me up on that. And I have stopped selling them because it's too much hassle. In other words, if somebody orders one, well, you feel really good, they want my print. And then all the work starts. You got to get it printed, you got to sign it, you got to get it mounted, you got to ship it. Oh my goodness, I've got a day job, I can't do this. So I stopped selling them that way. They can be bought from Science Photo Library as files, and actually you can get the file from me too and make your own print. I'd be happy to give it to you. So these are large format prints. They're like 8,000 pixels across, and they're very high resolution. They stand up very well to large sizes.
Oh, I have one in my office I'm very fond of, so I highly recommend it. Other questions? Actually, I
So
think, go ahead.
one last thing I'd like to say, I have quite a few undergraduates working with me and have had over the years, and mostly we put them on branch flow projects because it's very accessible. The simplest way to do branch flow is with Photoshop, actually. I haven't got time, I'm sure, Bob, but I could show you how to make a branch flow image with Photoshop. All you need is, in fact, I don't know, is my screen still showing from the computer
We're
now?
looking at your arm and the ceiling.
Okay.
It's sort of abstract. It's not to your face.
You don't have the, just a minute. You don't have my computer screen anymore, I guess.
Oh, you can share your screen if that works from your point of view. You're allowed to do that.
Well, there was an image that you may have shown already, which was done in Photoshop. And
Is that of that paper? I can show that if you want.
yeah, it's
Out of
in
the
that
Physics
paper.
Today paper?
Figure
Oh,
3.
okay. Yeah, just a second. Okay, here we go. Bingo, bingo. Share screen. Figure 3.
Figure 3.
Here it is. That one, right?
This one. Yeah, so that picture was done in Photoshop, and it is the essence of branch flow. It's actually a slice of branch flow. And in frame 1 is just a pattern I made with dots and colored lines. In frame 2 are the 2 and 3 are the essential parts of branch flow. First thing that happens is, if you think of momentum as it's labeled there in the vertical axis and position in the horizontal axis, the first thing that happens is momentum gets a kick up and down, sort of randomly, with some sinusoidal-like pattern. Then it drifts, and the higher momentum, for example, the red line, goes to the right, and the lower momentum goes to the left, and that's what happens. Okay, that's fine. But after a few more kicks and drifts, you get the bottom picture there. Gorgeous mixing of phase space, stable regions, unstable regions. And if you project down the red area, for example, you see that the redness would not be uniform. Those red regions are the branches forming. So the essence of kick and drift can be done, the essence of branch flow can be done by kick and drift in Photoshop.
A graphics program, not a computing program at all. Yeah.
Yes, it's just Photoshop on them on whatever platform. And the mathematics of this picture, you think would be for all to see, but actually it's quite subtle. Some of it is not understood. There are regions you see that are stretching badly, very thin, long lines, and other regions that more or less hang together. How many of those are there? What is their stability? This affects the transport across random media. And maybe the last thing I should say about it is we are very lucky to have Bob to have been forced into doing this. And it's astonishing that nobody had done it before, except perhaps Peter Bisky, but that was just one singular thing in his thesis. It didn't make it into his paper with Cord like it. So this it's odd that the early part of branch flow, where you get these V-shaped cusps, they're called, is well studied. The latest part, which I didn't show much of, is way, way off in the distance where the motion is really random every which way. What nobody had studied before was how you get from one to the other, from the first bad focal point, which is really what they are, to the random motion far away. You have these gorgeous branches. They're universal. And if you're interested in doing a project in this area, I'd be happy to help you. It's very simple. And there are unknown things you could discover. We discovered many things just visually. So this is a I don't know, one of the best chapters in my life in science is this project that started with Bob.
Oh, thank you. Very nice. The other questions? It is a lot of fun, particularly with talking with other people. It turns out what you find that's interesting in art, something that kind of grabs you and you're not sure why, that a lot of times you can bring that backwards into science to think about if it really relates to something physical or waves in some sense, that sometimes it makes sense the other way. That is, if you go from some patterns that you're seeing and you think, how did this really happen, and be able to use that for something. Okay,
Any
one
other
last,
questions?
go ahead. Yeah. One last question. I'll just ask a last question. Rick, did you used to own an island?
No.
You didn't?
Why?
I thought you did. Oh, in Seattle?
I owned a sailboat.
Oh, but you lived on an island.
I lived on an island, yes.
That was nice. Just say a little bit of what that looks like so everybody can feel bad that they don't live there.
Well, no, I lived on Bainbridge Island across from Seattle. And it was a lovely life. I had a beautiful home there. And I left all that behind to come to Harvard. And boy, was it worth it. So I just, I was going to show you another
Recording in progress.
Oh, sorry, that's my audio on two devices. That's a bad idea.
Oh, they were going sci-fi here.
Yeah.
Well, let me stop the recording and then we can wind things up. Stop share. Here we go.